Hello, this is a screencast on Poisson random variables. This is a topic I started talking about in class, and we ran out of some time. I'm not sure how central this random variable is going to be to the work that follows, but it's certainly interesting. I thought you would enjoy this, so I thought I'd make a screencast and share some details with you that we wouldn't otherwise see in class. So what's a Poisson distribution? Well, consider a random variable with omega, its sample space, to be the set of all counting numbers from 0 up to infinity. So it's an infinite discrete random variable. We say this random variable is Poisson if its probability mass function has this form, where lambda is some positive number, and we say lambda is the one parameter for the random variable. Think back to when we talked about the binomial random variable. It has two parameters, an n and a p. P is the probability of a success in the Bernoulli trial. N is the number of Bernoulli trials. And I, for a binomial, would be the number of successes we want to happen in the n Bernoulli trials. So binomial has two parameters. The Poisson has one parameter, a lambda. And this is the probability mass function. E to the minus lambda times, so this is like a scaling factor, times lambda to the ith power, all divided by I factorial. So let's check and verify that this function pi is indeed a probability mass function. The two things we need to check are all the probability mass functions positive, and do the probability mass functions all sum to unity, sum to 1. So I claim it's clear that each of the pi are bigger than or equal to 0 because it's a product of positive numbers, and so it's got to be positive. And to show that all of these probability mass functions sum to 1, I'm going to demonstrate it to you. But before I do it, I just want you to remember that the function e to the x has a power series expansion that's the sum as I goes from 0 to infinity of x to the I over I factorial. And that should look a little bit familiar. So here we'll sum all of the probability mass functions over all of the entries in our, or all the elements in our sample space. So this kind of summation, I can rewrite that in the standard form because our elements of our sample space are the numbers 0 up to infinity. And here's the formula for the probability mass function that's on the previous slide. So we can pull that e to the minus lambda out of this series because this series converges. You can use the ratio test and you can see the series converges. Converges absolutely, in fact, for any given lambda. So you can pull the e to the minus lambda out. And then this, right, has the same pattern as this. So this right here is e to the lambda. It converges to e to the lambda. So we'll rewrite this infinite series with the value, its a limit. And then look at that. Those exponents cancel out and you're left with the number 1. So indeed, the probability mass functions sum to the number 1. Pretty slick. So let's look at some properties of the Poisson random variable, stuff that's important. And I think the texts that I've read, the readings that I've shared with you, suggest that one of the functions the Poisson random variable has is to approximate a binomial random variable. Looks like I've got a typo here. There should be a k. If p is small and n is large, so that n times p is a moderate in size, I don't know what moderate means. I think you just have to have a feeling for how these work. But if p is small and n is large, so n times p is moderate in size, then the binomial probability mass function is approximately equal to the Poisson probability mass function. In the case where we take the parameter for the Poisson to be n times p. Okay, so if you wanted to, we could just substitute the n times p in here for lambda to be more specific. So that's an important property of the Poisson random variable. And notice you go from a case where there's two parameters, p and n, to a case where there's one parameter. And it simplifies computations, I guess. Speaking of computations, R can do a lot of these computations for us. In class, I told you about how you can use R to calculate binomial numbers, binomial probabilities from a binomial random variable. So d binom is the function. You've got the parameters n and p, and then I, there's the number of successes. So the syntax for the Poisson random variable is very similar. D Poisson, the D certainly stands for distribution function or distribution mass, probability mass function. And you've got a place for the parameter lambda, and then I is the number of events. So just for fun, again, typo. Just for fun, let's explore this approximation. So let's choose some values of the parameters for a binomial and some parameters for k, and compare the value of the binomial random variable to the value for the associated Poisson random variable. So here I've got a column of n values and p values, some choices of k, then I calculate n times p and set that equal to lambda for my Poisson variable. And you can see I compare the values. So here for n equals 10 and p equals 0.1, you can see that the binomial and the Poisson, they agree to one decimal place, and they're not too far off in the second decimal place. Same thing goes here for 20 and a probability of 0.15 for k equals 3. Okay, those are pretty close. Then here for n equals 20 and p equals 0.15 with k equals 8. Those are also very close in absolute sense. And then when n equals 30 and p is 0.05, lambda 1.5, then you can see that these values are really indeed close. So these two columns should show you what we mean by this approximation. No, they're not exact. They're not like blow you out of the water good approximations, but they're approximations. So that's often how we think of a Poisson random variable. So let's calculate some of these descriptive measures of random variables that we like, the mean and the variance and the standard deviation. Here I'm going to start the calculation for the mean of a Poisson random variable. So the definition of the mean is the sum over all the members of the sample space, that's k, times the probability that k occurs. So we'll use the formula for the probability mass function. We get this. And now we're going to do a bunch of algebra. So I'm going to pull that e to the minus lambda out, because again, this series is going to converge absolutely, so we can do that. And then I'm going to cancel this k with the k down in the k factorial, so I'm left with a k minus 1 factorial. And then I'm going to pull a lambda out of the numerator right here, so that my exponent in the numerator is k minus 1. Now you'll notice up here in the definition for mean, I've got k, and my k starts at 0. So what happens is that 0 times the probability mass function for 0, right? That's not even part of the summation, so might as well start at k equals 1, and you get this. That's what I did. But down here, you'll notice what happens is that you can re-index, right? So if I decrease my index by 1, as I did here, from 1 to 0, then I have to increase my indices in my formula by 1, so I get this. And look at that. There's the power series for e to the lambda. So I throw that in there, and again, you get the nice cancellation, and I'm left with lambda. So the mean of a Poisson random variable is its parameter lambda. So let's calculate the variance of a Poisson random variable now. Here I'm using the alternate definition of calculating the variance. You'll remember that the first definition, the definition from first principles, would look something like this. But there's you can do some algebra, and you can see that this is an alternate definition for it. And yeah, we can talk about that more later. So plugging in the probability mass function for p of k, right here, this is what the expression becomes. And now I'm going to just do some manipulations. Play a similar game. One of these k's, I'm going to cancel with the k down here. And then the remaining k, I'm going to write it as k minus 1 plus 1. Oh, and you'll see also here, I pulled a lambda out from the numerator, right? Since the denominator becomes a k minus 1 factorial, I go for that symmetry upstairs by pulling the lambda out there. And now what I'm going to do is I'm going to distribute this summation across these with this factor and then this. So we've got this summand and we've got this summand as a result. So in this first term, we re-index, and I get this expression, and this is the probability mass function. So this is just an expression for the mean of my random variable, so I can replace this whole thing with lambda. This right here is an expression for e to the lambda, right? I can pull this back out, and then the whole thing becomes e to the lambda, and then they cancel, so I'll just be left with a lambda. And I got that lambda squared there. So that's how it simplifies. And then this cancels with that, and I'm just left with a lambda. Okay, so the variance of a Poisson random variable is also the parameter lambda. Pretty slick. So mean is lambda, variance is lambda, and the standard deviation is the square root of the variance, so the standard deviation is the square root of lambda. So we can plot probability distributions for visualization, and here's how we would do it with the Poisson random variable, and I talked about this in class a little bit. First, we'll make a vector of the values for I that we want to calculate the value of the Poisson random variable for, and this is what we're going to do. We're going to plot, so that the argument for plot is you put in your x input values, and then you put in your output values. And so the output values are going to come from the d Poisson function. I plug the success vector into that, and it's going to give me a vector of values out. Here I've got for lambda equals 5, and we'll have the plot on the next slide. So there we go. That's what the Poisson random variable for lambda equals 5 looks like. Notice right here, 5, right there in the center, right? That's the mean. And so that's what we come to understand. You can see that the variance is also lambda is 5 in this case. And so the spread is largely contained within 5 units of either side of the mean. I'm just kind of waving my hands with that language, but you can kind of see that most of the mass of the distribution is within 5 of the mean. So this is the Poisson random variable. You saw some calculations and derivations of its mean and variance and standard deviation, some ways to use R to calculate it, and a way to visualize it. I hope you'll be able to make good use of this as we go forward in the course.